mapping, well, not mapping people to the printer, but making sure that people have access to local services like their file share or print server and things of that nature. So a typical CCNA, that's what they're going to be focused on, networking in the enterprise. Now, obviously, we can move up, do networking just in the ISP. We can become a cloud network engineer. But I mean, really, cloud network engineering, that kind of is the enterprise now, right? That is our modern enterprise. We may own or rent things from the cloud as an organization. That's our resources. Okay, moving on. So the history of the internet. So the very beginnings of the internet started with something called ARPANET, which was just a it's DARPA, which is still around, DoD-funded program between universities to establish a line of communication, and we call that the internet. So in 1983, TCP/IP became the standard, and that's still what we use today. We still use TCP/IP protocol suite to route traffic across the globe. That is the standard technology protocol we use. Now, obviously, IP has two versions, V4, V6, that we're going to dive into today. So your role, before we end this slide, your role in networking. So as a CCNA, it is your job to ensure that the critical infrastructure that connects us stays online. So that's it. At the end of the day, you're making sure that the network internet is highly available to your users. As IT professionals, we enable the business and business operations and try our best to become assets to the organization to make our businesses profitable. As network engineers specifically, as part of that big IT infrastructure, we make sure that the network and everything in between becomes highly available. With that, we have network infrastructure we're going to learn about. That is the basics of network engineering. Our switches, our routers, our firewalls, our access points, and wireless LAN controllers. We maintain, monitor, and manage those and all the third-party applications that come with it, or the monitoring systems that come along with that. Our software-defined networking infrastructures that comes along with that is now part of our role. It's our role to make sure that we consistently automate and improve our network while maintaining that high availability for our customers or our organization. Whew. All right. Network engineering. And yes, it is cool and it's very fun and it does make you pretty good money. All right. Let's move on. So now let's go over the different network components. Let me pause for a second, guys. Let me make sure I got my whiteboard up. Give me 1 second. Okay, let's continue. So now let's go over the different network components. So the network enterprise / infrastructure. So network professionals will manage and maintain key network hardware. And in this course, we'll focus on network components that Cisco wants us to learn about. So really what we mean by that is what's in the CCNA exam objectives that we have to learn about. Meaning, it's just the basics. It's CCNA, right? So we're going to learn about layer 2 switches, multi-layer switches, routers, the basics of firewalls. Where did this go? Okay. Sorry, I'm just in the background getting something prepped for us. Okay, so the first thing we'll learn about is a switch. So what is a switch? This is a networking device that forwards data packets, frames, locally within a LAN. Now, I know we're diving right into it, so we haven't gone over what the OSI model is, but we'll talk about the layers here when talking about these network components. So what I'm going to do now is I'm going to share our whiteboard because I like to draw for you guys so it's not super boring, right? Okay. All right. So let's check it out. So what is a switch? So this is going to be a layer 2 device that's going to switch packets, and what we call packets at layer 2 is frames. So a switch is going to switch frames in our local area network. A switch does this by maintaining a MAC address table. A MAC address is that 12 hexadecimal address that's going to identify physical devices or your NIC in our local area network. So let's draw this out. So this switch, let's say it's connected to PCA here. Now PCA is going to have a network interface card that's going to connect to this switch. So at this switch, let's say it's 24-port switch. This is going to be gigabit Ethernet 0/9. PCA is going to have a NIC that's going to plug into this LAN connection, RJ45. That NIC is going to have a burned-in address or a MAC address that's going to identify it in this local area network that I'm drawing up here. So for brevity purposes, I'm just going to say that this MAC address is AA. But we know that MAC addresses are hexadecimal, which means that's going to be a 12-digit number from 0 to 9 and A through F, okay? So that's hexadecimal. 0 through 9 and A through F. So A, B, C, D, E, F. So like A equals 10, B equals 11 as far as numbers. So instead of going up to 10 after 9, we go to A. That's hexadecimal. Every single device is going to have a MAC address. Even your phone, when it's connected to the cell tower, it's going to have a hexadecimal hardware address or MAC address. Now PCA, when it wants to communicate in the network, it's going to create an Ethernet frame. So 802.3 is the Ethernet standard that we're going to use to talk in our wired networks. So 802.3, that's the Ethernet standard. So we're going to create an Ethernet frame. From the PC, we're going to generate that. That frame is going to have what's called a layer 2 header, because switching and frames and MAC addresses is a layer 2 technology. So PCA is going to generate an Ethernet frame. That frame is going to have a layer 2 header. That layer 2 header is going to have a source MAC address and a destination MAC address. So the source, being us, is going to be AA. And the destination is going to be whoever we want to talk to. So let's just draw up another PC here. Let's just say it needs to talk to PCB. And that MAC address is BB. Okay? So on our layer 2 header, our destination MAC address is BB. And then we're also going to have, of course, our data payload. So I'm just going to put payload. Let's just say this is anywhere from like 64 to 1500 bytes in size. Don't worry, we're going to go over bits and bytes when we get to IP4 addressing. And then at the tail end here, we'll have an FCS field. FCS field. That's the frame check sequence. That's going to be doing exactly that, frame check sequencing, making sure that things aren't coming in with like CRC errors, cyclic redundancy errors, that it's coming not fragmented. Okay, that's a D, payload. People always say my handwriting shit, so I'm trying to be aware of it. You know, let me fix that, because you guys are going to get access to this whiteboard as well. Data payload. All right, so there's our layer 2 Ethernet frame. Now when PCA sends this to switch 1, two things are going to happen. Or the switch. I gave it the name switch 1. So this switch is going to maintain what's called a MAC address table. So this is going to be a MAC address table, otherwise known as a CAM table, which stands for Content Addressable Memory. I'll write that out in just a second. But in that MAC address table, we're going to maintain a state of known source MAC addresses and the ports that correlate with them. Also a VLAN, but we're not there yet, okay? We'll just stick with the basics. So what a switch does when it feeds the Ethernet frame, it's going to take that ingress or source MAC address and populate a MAC address table. So on port 0/9, it's going to be AA, okay? Now let's say PCB has already previously communicated with the switch. So we'll also have on port 010, we know where PCB is. So step one, the Ethernet frame hits that switch. It's going to look at the source MAC address table. Sorry, it's going to look at the source MAC address and insert it into the MAC address table. And then it's going to take a look at the destination MAC address here, and it's going to reference that MAC address table and say, do we know where to send this? Do I know where to send to MAC address BB? Well, let me check my MAC address table. Yes, I do. MAC address BB lives on port 10. So then we forward that frame to the destination. That is switching in a nutshell. That's as simple as I can make switching at its root. A switch uses a MAC address table to make intelligent forwarding decisions, and it populates that MAC address table based on ingress or source MAC addresses from its active users. This MAC address table gets flushed unless otherwise configured, like, statically saying, hey, this MAC address will always live on this port, every 300 seconds. Yes, I say 300 seconds because that's how you're supposed to learn it, in seconds, but that does equal 5 minutes. It gets flushed. Okay, now this is how we forward with a known MAC address. So we think about this. The switch knows where MAC address BB is. That's where PCA is trying to talk to. But what if it doesn't know? What if the switch doesn't know where the destination MAC address is? Well, then it's going to do something called frame flooding. That's where the switch is going to send a broadcast MAC address out to all active interfaces besides the one it came in on. And in that broadcast, it's going to be asking, who is BB? Who is this MAC address? And hoping it gets a response. So this diagram here is known MAC addresses. But when we're doing unknown forwarding, meaning the switch doesn't know where BB is. So let's erase this here. Let's say it doesn't know where BB is. It's going to do something, a process called frame flooding. So unknown, I'm going to type this out too so it's a little bit clearer. So unknown destination MAC address. We're going to do something called frame flooding. That's where we send a broadcast MAC address. And the broadcast MAC is going to look like this. All Fs. You need to know this, okay? It's going to be very important for network, switching fundamentals. It's going to send a broadcast MAC address out all active interfaces besides the one it came in on. So what do we mean by that? Essentially what we're saying is, hey, PCA wants to talk to this MAC address BB. Well, I received that frame. I referenced my MAC address table. I have no idea where MAC address BB is. So I am going to instead send out a broadcast MAC address. So I'm going to take that all Fs, put it in the destination MAC address, and I'm going to send that out all my interfaces. Besides gig 09, because that's where the request came in to talk to this unknown destination MAC address. So I already know that's not going to live there, right? So I'm going to insert these all Fs into the destination MAC address field, and I'm going to send that out all active interfaces to find out who BB is from my original request. And then once BB responds, basic switching fundamentals, that MAC address responds. It's going to respond with an Ethernet frame, and its source MAC address is then going to be inserted into the MAC address table. And then now we know where to send it. So with unknown destination MAC addresses, we do a process called frame flooding. We send out a broadcast MAC address, all Fs, out all active interfaces besides the one it came in on. I keep emphasizing that, probably for good reason. Okay, that's switching. I need to rest my voice, guys. So let's go ahead and take a 10-minute break. We'll come back at 10:10, and then we'll continue. Okay, let's go ahead and get back into it, guys. So we just finished up switching. So just a couple more key notes that I kind of wrote down here. So switches forward based on frames. Frames have a layer 2 header with a source destination MAC address. Switches can also be multi-layer. So we can have multi-layer switches, which pretty much means we put IP addressing on the switch and give it some layer 3 IP capabilities. So some switches can do routing. Well, I say some. Any switch, we can configure routing on it. Out of the box, a switch is layer 2. So like in a test environment, what layer does a switch operate in? Layer 2. Real world environment, we know we use core and distro switches to do routing, in our campus networks. But anyways, that's the real world. I don't know if they'll be, asking that. But yeah, switches can also be multi-layer. Another key thing, do not forget these notes over here. Unknown destination MAC address. You need to know what happens in that scenario when a switch gets a request from a user with an unknown destination MAC address. You need to understand that process. Okay. Now, moving on. So now we're moving on to a different piece of network infrastructure. Remember, this slide deck we're technically on is network components. So we're going over all the hardware that we may manage, maintain, configure in our networking environment. So now we're moving on to routers or IP-based routing. So moving up a step in the OSI model, routers operate in layer 3. When routers forward data, we call that a packet. A packet, an IP-based packet, is going to have a layer 3 header with a source and destination IP address that doesn't change. A router maintains a routing table which knows information from its routing neighbors, and it'll use that routing table to properly forward traffic to get to the destination. So here's how it flows. We can kind of look at this like the life of a packet. So R1 is connected to R2 here. Through some sort of static route or administrative configuration, or through some sort of dynamic route, R1 and R2 are going to share routing information with each other. So they're going to have this shared link here. Let's just say this is the IP address. So over here is .0. Over here is .1. Okay. So R1 and R2 have IP reachability between each other. Let's say we configure a dynamic routing protocol. I know we're drinking from a fire hose here. So we configure OSPF. When these routers are configured for a dynamic routing protocol, they're going to share routing updates with each other. So they're going to share information, the networks they know about. So I'm just going to put in here routing update, which really just means R2 and R1, they're speaking the same language when it comes to routing protocols. So we configured like OSPF here. R2 is going to tell R1 about the networks it knows about. And if it had any downstream neighbors here that we can't see, it would relay the information about those downstream neighbors' networks as well. So R2 is going to tell R1, hey, I have the 10.0.1.0/24 network. R1 is going to do the same thing. It's going to tell R2, hey, I got the 10.0.0/24 network. They're going to share that with each other. They're then going to individually build what's called a global routing table. So R1 and R2 are both going to do this. They're going to build a global routing table. Otherwise, sometimes known as a RIB, or that's another name for it, routing information base, they're going to build a routing table based on the networks they know about and the information they get from their neighbors and from a routing protocol. So R2 shared with R1 a routing update of 10.0.10/24 via OSPF. R1 is now going to insert that into its routing table, and now it knows where to forward any requests from its users if they're trying to reach this network. So in this routing table, here's what it's going to look like. I'm going to put this in red. So it's going to say, hey, I got this routing update via OSPF. So we have this little code here. It's an O for OSPF, routing table code. And it's going to say, hey, if any of my users want to reach this network, they're going to go out gig 00. That's where I learned it from. I got the routing update on this interface. And then there's also going to be some other things here called administrative distance and metric that we're not going to talk about yet. Also on R1's routing table is going to be the local and connected routes. So it's going to have 2 local routes, or networks, I should say, prefixes or networks it knows about. So R1 learned about this network from a neighbor, R2. But it also has some local stuff it knows about, right? Because 10.0.0.0/24 is connected to it. And let's just say this is gig 0/1. And then also this network, 22220/31, is also local. It's connected to it. Okay, so this is not exactly how a routing table will look. I'm missing some information on there, but we're not in our routing section yet, so we need a deep dive. This is the router's entire goal. Build routing tables so that it can route IP-based packets for its users. Now, let's talk about a layer 3 packet, or an IP packet with the layer 3 header. So PCA here. Let's say PCA wants to talk to PCB. What is it going to do? PCA is going to create an IP-based packet. This includes a layer 2 header, because we don't just, an IP-based packet is going to have a layer 2 header and a layer 3 header, and also a layer 4 header, but we're not there yet. Right now, I'm just focused on the layer 3. I'm going to draw the layer 3 header, but just know encapsulated in there is also a layer 2 header that's on the outside of it. Think of like an onion, right, with its layers. So layer 2 header, then layer 3 header. But just for this scenario, so PCA wants to talk to PCB. So it's going to create an IP-based packet. That layer 3 header, and it's also going to have its data payload as well, okay? Just going to put data here. Remember, let's just say this is 1,500 bytes. This is going to come into play. We're going to talk maximum transmission unit. Sorry, okay, I need to go a little faster. Hold on. So we're going to have a source IP and a destination IP. So the source IP is going to be us. The destination IP is going to be PCB. That's who we want to talk to. So we create our layer 3 header, and we send that to our default gateway, which is R1. When R1 receives this, it's going to look at the destination IP, and it's going to say, okay, you're trying to get to 10.0.1.50, 10.0.1.50. Let me reference my routing table, and guess what? I know where to send you, because I know about the 10.0.1.0/24 network, and 10.0.1.50 lives within that subnet, and I learned about that via gig 00. I need to send you that way. And that is IP routing in a nutshell. That's how it works on a very slimmed down scale, but at the fundamentals, that's exactly how it works. Routers use routing tables that are built off routing updates from their neighbors using routing protocols to know where to forward traffic for their users. That's the basics of IP-based routing. Now, routers can also have additional features. So Cisco has what's called ISR, which is Cisco Integrated Service Router. And besides just doing layer 3 routing like I just showed and described to you, it can do like VPN connections, remote access VPN concentration. They have firewall capabilities. The router has access control lists and filtering capabilities. It can do like Call Manager Express. So sometimes routers can be an all-in-one appliance for like monitoring and other things like that. Eventually through this course, I'll show you a Ubiquity router. I know it's not Cisco, but just to show you, I have like an enterprise-grade router in my office here. I'm in my Trepatech office. And that router, besides just doing routing, does a lot more for us. And Cisco also has platforms that do the same, that do more than just what I showed you. But at its base function, that's what we're worried about a router to do. Route IP-based traffic and send it to the correct destination on the best path. More on that later when we go over routing probably tomorrow. Okay, the next network component we are going to talk about is a firewall. Oh, let me type this out. A firewall. Should I zoom in on this thing? It's always a love-hate relationship with this whiteboard. I like it. Like I have so much functionality, but sometimes... Okay, so now let's go over a firewall. And I'm going to put key notes for this firewall because it's kind of, we're here to pass an exam. So this is going to filter traffic inbound/outbound. Yeah, that's pretty much it. Filter traffic inbound and outbound. It's going to create security zones. So firewalls create security zones like inside and outside. And it's going to filter based on the following, depending on the firewall. It's going to filter based on IP-based traffic, the port/protocol. So filtering based off like, hey, I'm denying telnet. Or it could be context aware if we have a next generation firewall and do deep packet inspection. So when we're talking firewalls here, I'm going to go with the traditional sense. A traditional firewall for our enterprise, what does it do? What does it look like? So let's draw that out. So a traditional firewall, when it comes to a traditional network infrastructure, is going to sit right there in between our customer edge router and our and our provider edge router. So this firewall is going to separate our intranet and the external net and consider one zone trusted and secure and the other zone untrusted and insecure. So there's our firewall. That's going to be connected to our router here. And then that router is going to be connected to like our distro switches. And we're going to have our campus network here. And then this is our intranet, right? This is our internal enterprise. So this zone is going to be considered our trusted inside zone. And remember, this is a CE. This is our like customer edge router. Now here, maybe this is like, this firewall could also be doing our routing for us, maybe. But this is our trusted inside zone. And then this is going to be connected to the ISP. And this is going to be considered our outside zone. This is going to be considered our outside / untrusted zone. And we're going to be filtering traffic, inbound and outbound, from our inside internal network here. That's a firewall's main purpose. Now, how it filters is up to us and how we configure it. So are we filtering based on IP, ports and protocols? Are we doing some deep packet inspection, some context awareness, maybe enabling some machine learning on that firewall? Maybe we don't have a dedicated firewall appliance anymore. Maybe we have something called SASE, which is like Secure Access Service Edge, or the firewall is part of like a unified system that does like our SD-WAN and other capabilities. Anyways, more on that later. This is just CCNA, keeping it simple. So that's what our firewall does. This is like a traditional firewall hardware appliance that's going to sit at your office building, that's going to be protecting your environment for you on the network, inline on your network. This could also do other things though. This can track VPN connections, can be a VPN concentrator. Okay, moving on. I don't want to get too deep. Okay, next, I'm going to go back to the slide deck for this one. So let me now share the screen. Where's my slides at? Okay. All right. Am I sharing my screen? Yes. Okay, so now let's go over an access point. So this is a Wi-Fi access point we're going to talk about here. So wireless access points at their root. Now we're going to learn, and there's a lot of different things about access points that we're going to talk about. I'll bring up the whiteboard again, but this enables us, an access point, to have Wi-Fi enabled devices communicate on our wired network. Meaning, access point sends out a Wi-Fi signal, our Wi-Fi enabled devices connect to it, and that gets us access to our network resources. Now, access points are not all made the same. More than likely, you guys sitting at home have an autonomous access point that's sending out a Wi-Fi signal that has a modem inside it, and it has a router. It's doing switching for you, does some port forwarding and some firewall configuration for you. We call that an autonomous access point. That's perfect for your small home office and that broadband connection, because you may be connecting to a shared fiber connection or a shared broadband connection in your neighborhood. That's an access point. We also have more enterprise-grade access points called lightweight or cloud-based access points, where that access point, its main purpose is just to connect Wi-Fi enabled devices, and it's going to be controlled by a centralized server or some sort of service in the cloud. And those access points, we call them lightweight or cloud-based. And they rely on some sort of centralized controller to send them their profiles, what SSIDs they're going to broadcast, what wireless local area networks, and what kind of wireless security they're going to have. So an access point can be configured and managed in several different modes: autonomous, lightweight, and cloud-based. And they're usually manufactured and purpose-built to be one of those 3 different modes. So Cisco access points primary purpose is to wirelessly connect endpoint devices to what we call the distributed network, which is wireless vernacular for just the wired switched infrastructure, our backbone infrastructure. Okay, let's head back to our whiteboard here. So let's talk about our access points. Zoom in here. Access points. They have 3 modes. They have autonomous, mode, lightweight mode, and cloud-based. So with autonomous mode, this is going to be for our small office, home office environments. So small office, home office, SOHO, you're going to see that acronym. Okay? They're going to do all the routing. They're going to do the switching. And they're going to be doing some firewall functionalities all in one, along with just, sending that Wi-Fi signal. So that's what an autonomous mode access point does. It can be meshed for some scalability. Now, when we say scalability, we mean like, oh, hey, like I got this small office here, and in the back of our office, the signal kind of goes dead, and I'll just put another autonomous access point up and we'll mesh it. Or that's like a Wi-Fi extender you have in your house. You got a big house, you do a little Wi-Fi extender. That's what we mean by some scalability. Maybe we can do some sort of mesh. Okay, lightweight mode. This is going to be controlled by a wireless LAN controller. Highly scalable for huge enterprises. So when you go to a football game, go to a basketball stadium, go to the airport, this is the access point you're connecting to. Lightweight access points that are in this huge infrastructure and network working together. Where if I'm walking from terminal A to terminal B and I'm staying on the Charlotte Wi-Fi, that's a horrible airport, or Raleigh, and I'm connected from terminal B to terminal C, that's lightweight access points being controlled by a centralized server called a wireless LAN controller that's pushing all the profiles, all the configuration for those access points. That allows me to roam. It's going to tell the access point what kind of security it's going to have. It's going to tell the access point what wireless local area networks to broadcast for and what SSIDs correlate with that. It's going to apply some quality of service on those access points. Say, hey, this SSID, when you just connect, apply this quality of service profile. So I'm saying all that almost like a pretext to what you're going to learn later, right? And then cloud-based is going to be controlled by a cloud service or dashboard. So what I mean by that is, like, the big one is Cisco Meraki. We buy Cisco Meraki access points. We put them up on our ceilings. We connect them to a switch. And then from our laptop, using an internet connection, we go to our Meraki dashboard, and that's where we control those access points. Compare that with the wireless LAN controller, where yes, we may access this wireless LAN controller via an internet, a GUI, from our web browser, but we do that from inside our network. That's an internal on-prem server that we maintain, manage, and monitor and control that physical piece of hardware and everything in between that. It's software updates, everything. With a cloud-based controller, that's maintained by a cloud service provider that they have their own data center, and you can access your Meraki dashboard from anywhere. You don't have to be inside your enterprise to access it. But this is also scalable for medium to large enterprises. So that's our access points. Now, let me draw out for you lightweight mode access points, because our next slide we talk about wireless LAN controllers, which is something we have to maintain as part of our network components and infrastructure. So let's draw this out. So I'm going to show you what a typical campus network design is going to look like. This is basic. This is like the perfect network. This is how we're going to do it for the perfect amount of users. Okay, it doesn't always look this clean in the real world. So we're going to have what's called our distro switches. These are big, beefy, multi-layer switches that are going to be doing the routing, ACL, and managing VLANs for us, like the default gateway for our VLANs, our segmented networks. So we're going to always have them in like a redundant pair. So this is distro switch 1. This is distro switch 2. And if we have server farms, some on-prem data center services, whatever the case may be, they're going to be connected to those distro switches. And in this case, we do. We have our wireless LAN controller connected here. Wireless LAN controller, which is going to be provisioning, controlling over access points. Now, hanging off that distro layer is going to be our access switches. So these is typically going to be our layer 2 switches that our endpoints are connected to. So we connect our printers, our VTC machines, our phones, our computers to these switches. What else do we connect to these access layer switches? We connect our access points. Oh, that's a bad drawing of it. Our access points also get connected here. Okay. So now, remember, we're talking about lightweight mode access points and our wireless LAN controllers. Let's say we have 2 VLANs, 2 networks in our campus organization here. Our campus enterprise, we have 2 networks. So let's say we have VLAN 10, and this is for like accounting. I don't need to write that out, but we have VLAN 10. Here's its IP address, 10.0.0.0/24. And then we have, we'll put this in purple, VLAN 20. That's going to be 10.0.2.0/24. Now we have these VLANs. So when I connect a user via Ethernet cable to this switch, I'm going to assign it a VLAN, right? I'm going to say, hey, switch port mode access, switch port access VLAN 20 on port 10. And this is for our sales team. So if a sales user plugs into this switch, I need to put it in the sales VLAN, which I'm designating VLAN 20. And VLAN 20 correlates to this network. But how do we extend that to wireless? Because we might have some wireless users that need to connect to these VLANs. So from the wireless LAN controller, I'm going to make 2 wireless local area networks that are going to correlate to VLAN 20. And in those wireless local area networks, I need to set an SSID. That's a service set identifier. That's what you connect to. That's what you connect to on your phone, on your laptop, when you connect to your Wi-Fi. You search for an SSID. That's what the access point is broadcasting. And that SSID correlates, write this down, that SSID correlates to a wireless local area network. A wireless local area network correlates to a certain VLAN or network segment in your backbone environment, your wired environment. So this SSID, we'll just call it sales Wi-Fi. Okay? We're going to have another wireless, and also in here, we're going to set like our Wi-Fi security. That's horrible. Let me write that better. We're going to set like our Wi-Fi security. We're going to set up our QoS profile. We're going to set up our type, which means like enterprise or PSK. So we're going to sign in with a password or a username and password. We set all that up in this wireless local area network. And then we're going to push this configuration. I'll put some more shit in here. our radio configuration, which means what kind of Wi-Fi standards are we going to use. So like 802.11ax. Are we going to have band steering enabled? So are we going to allow our users to connect to our 2.4, our 5 gigahertz range? Because that's the two major ranges we use in like 802.11ac and AX. We have the 6 gigahertz range now, but anyways. So we build this wireless local area network, and we do that from the wireless LAN controller's GUI. We build that in the wireless LAN controller. When we set up these access points are going to connect. Let me do this in blue. We're going to get them connected and onboarded into this wireless LAN controller. So they're going to connect to this WLC via what's called a CAPWAP tunnel. A CAPWAP tunnel. So this is going to be a CAPWAP control tunnel. In this CAPWAP control tunnel, we're going to connect to the wireless LAN controller. They're going to onboard us, and then they're going to push our configuration. So we're going to have two of these. We're going to have a wireless local area network for VLAN 10 and VLAN 20 for our sales and our marketing team, or whatever I said VLAN 10 was for. It's accounting, doesn't matter. And then each access point is going to broadcast an SSID that correlates back to these wireless local area networks. So this would be like our sales SSID, and this will be our accounting. So a single access point can broadcast multiple SSIDs that correlate to the wireless local area networks. And now when we have a user connect to the accounting Wi-Fi, that access point in the back end has another CAPWAP tunnel connected to that WLC. That's a data tunnel. So all this user's information, when it's sending traffic to the access point, is going to go through that data CAPWAP tunnel. And then the wireless LAN controller is going to decide how to route or switch that traffic. So this is lightweight mode. And this is very basic how we start beginning to set up a wireless environment for our enterprises. Whew, okay. Just like to get some wireless stuff out of the way early. And that's what a wireless LAN controller does. I'm going to go back to the slides because we have one more network component I want to talk about called SDN, software-defined networking. I want to do that on the slides. So let me share my screen. And again, yeah, this is going to feel like drinking from a fire hose. We got a lot to go over. Okay, so now let's talk about SDN, software-defined networking. Fridays when I say deep dive. Fridays when we're going to go over this a lot more. But anyways, so SDN controller, or what is software-defined networking? So software-defined networking is not the opposite, but different than traditional networking. Where traditional networking, we individually set up our routers and switches in our fabric, what we call our fabric, our hardware, our switches, our access points, whatever the case may be, routers, via the CLI. So we go in, individually configure them. And then those devices make intelligent decisions on what we call control, on the control plane, individually. Well, with software-defined networking, we centralize all those control plane functions into a single pane of glass or appliance. So an SDN controller-based networks are taking all that functionality that used to be individual at the device, putting it in a centralized place, and then we manage that individual controller, and that's going to make the routing, the policy, all the decisions for us. So controller-based networking is all policy-based and aims to create consistency in a network. So some of the offerings we're going to talk about, and this slide I need to update because it's not called Cisco DNA Center anymore, but for our enterprise. So all of our campus networks, our spine and leaf architectures, our wireless access points. For our enterprise, the Cisco SDN solution that we talk about is something called Cisco Catalyst Center. That's, again, where we have that centralized device that's managing our fabric and our underlay from a single GUI. On our WAN side, we're talking customer edge routers using multiple forms of transport to send traffic to the internet and to our other spokes and hubs and data centers. The Cisco offering we call that is SD-WAN, where we centralize control for all that. And then last network component we're going to talk about is an endpoint. So an endpoint is any device that a user uses in the enterprise to access the network. I know it's a little redundant, like what are we talking about here? An endpoint is everything a network engineer really doesn't touch, right? If the printer isn't working, but I can ping it, I can print the test page, and it's not working other than that, but it's on the network, it's reachable on the network, I'm done, right? If my user can send HTTP traffic to a web server, then I did my job as far as troubleshooting that web server, right? Or web services. That's what an endpoint is. Anything that a network engineer really doesn't touch, but it's part of our ecosystem that we need to know about. All right. So before we go on our next break, what I want to do is I want to show you what SDN kind of looks like from a Ubiquiti machine. So this is my office here. This is my router. What you see right here, it says network. This is my router that's literally down here in a little, not a comms closet. It's racked up. And I'm accessing this router via the web. This is a controller. This is my controller console. So here, I can monitor and view my topology, all the different devices. I can see its activity on here. I can go to this dashboard that shows me my network traffic, my top talkers. I can identify the applications that are used the most. I can come down here, and from this controller, my router, I can configure my ports. I have little ports in my router. I can come here to settings. I can set up different networks. I can set up my Wi-Fi, my different SSIDs and wireless local area networks. I can set up VPNs. I can set up different routing here, static routes, OSPF, BGP, NAT. So this is SDN. Instead of me going to a CLI and doing all this, show commands, I get this nice dashboard for me. This is software-defined networking. Okay, awesome. What? Oh, 10:42. Looks like I've been yapping a while. Let's go ahead and take another 10-minute break, guys. We come back, we'll move on to the next slide deck, next lesson. So if you've built a computer before, you know it has a motherboard, it has a CPU, it has its RAM, it has its SSID or NVMe. It has all those basic components. A router or switch, for the most part, is going to be laid out similar. In a router, one of the main differences is we're going to have something called flash and NVRAM. Well, really just flash instead of like a hard drive. That's where our operating system is going to be stored. And then, of course, we're going to have way more network interface cards. We're going to have our LAN ports and our WAN ports. And then in a switch, of course, we're going to have multiple LAN ports, 24, 48 port switch. And switches are going to have chips called ASICs, which are going to do the computing for our switches on a per interface basis. Something additional is we have ROM, which is read-only memory. That's going to hold diagnostic software used when the router is powered up. It stores the router's bootstrap program. This is similar to like the BIOS of a computer. This is going to do our checks on our motherboard, firmware, and our read-only memory is going to boot us into the operating system, just like a BIOS does on a computer. Now, the actual boot process. So here's the steps. So take a router switch out of the box. We boot it up. First thing it's going to do is this post check. It's going to check the inputs and outputs of the hardware, just like the BIOS check in a PC. Now, we don't have like a similar UEFI secure boot process, but post is like the same thing. And then we're going to load into what's called ROM, read-only memory. This is going to load our bootstrap program, and then that bootstrap program is going to search for an iOS. So it's going to search for the iOS in its storage, which is going to be flash, rather than an SSD or NVMe or a hard drive. We call it flash. If it doesn't find an iOS in flash, it's going to use TFTP. It's going to broadcast like the broadcast IP, which is all 255s, and search for an iOS. If it can't find a good iOS using either method, it's going to load into what's called ROM-mon mode, which is pretty much just like loading into the BIOS menu, right? Same thing, when the computer doesn't have an operating system, it boots into the BIOS menu eventually, right? It'll go through its check. It'll check for a hard drive, check USB. It'll check the Pixie environment, see if we can load an operating system over the LAN. Then if it can't, it either just keeps rebooting or it loads into the BIOS. Router or switch does the same thing, except it's going to load into the ROM-mon mode. Now, our storage device on our router or switch is going to store our iOS and also a file called the NVRAM. This NVRAM text file is going to store the startup config of our router and switch. So when we get into the CLI of our router and switch and we're making changes in what's called the running config, that's RAM. That's random access memory. And any change we make, if we don't save, we lose. Well, when we actually save, we type in the command copy run start or do write in our router and switch. What that's doing is taking the configuration and settings in RAM that is volatile, that it's cache information, that's the running config, and it's going to store it in a file called the startup config. That startup config is our NVRAM, our non-volatile RAM. Okay, awesome. So we're going to go to lunch, guys. It's pretty much almost 11. So we'll come back at 12:30 EST. We'll come back at 12:30, a little bit longer lunch today. And when we come back, get ready, because drink some caffeine, because we're going to go hopefully get into IPv4 addressing, finish IPv4 and IPv6, and then your homework tonight will probably be like subnetting, okay? So let's go to lunch. I'll see everyone at 12:30. I'm going to kill the Zoom call. I'll load it back up probably like 12:25. Okay, welcome back everyone. Hopefully you all had a good lunch. So we're going to finish up today and end at IPv6, and then I'll put all this in the Signal group chat as well. And the homework for today will be to watch the subnetting videos so that we're prepped and ready for tomorrow so we can jump right into VLANs and switching and get into our labs, okay? I don't want to overload you on the first day, so let's go ahead and continue. Okay, so network architecture. So this is going to be a section going over different ways we can design and implement our network infrastructure in our enterprises. So at LAN, I was talking about LANs even as a kid, having LAN parties, right, on our Xbox before Xbox Live was a thing. And that definition I was using as a kid that I didn't even know is still same today. Local area network means that it's in your little office. That could be your big campus network, but it is local. It's a collection of devices connected together in one physical location, in your home, in your huge office with 12 different floors, or in your single building. Now, we use this term not always to its the most accurately, meaning we don't always hold it to its exact definition. Sometimes we say LAN when we really mean our big campus network for a university or for a huge compound that we're doing network engineering administration for. But in general, we just mean it's local to us, meaning, hey, that's on our LAN, and we know that it's something we control. Sometimes we use the term LAN interchangeably with like intranet or enterprise. But really, the term LAN is typically used to describe a small office network or layer 2 switching infrastructure. As we get larger in our enterprises, we just call it our enterprise or our campus network. But be aware that sometimes people will use this interchangeably. I would consider the architecture I have of my router, my Cisco Catalyst switch I have in my office, I got 2 Ubiquiti access points, and like 40 computers. That's a LAN. Now, if I owned this entire strip mall, the strip mall down the road from here, and I had multiple different sites, I would call that like a campus network. Okay, a WAN. So every enterprise is always going to have a WAN connection. So typically when people hear WAN, they think internet. That's not always true. Really, a WAN connection is any connection, whether that be a VPN, MPLS, dedicated circuit, serial connection, a antenna connection. A WAN is just router to router or connecting you to another network. So a wide area network, by definition, is a collection of interconnected local area networks. As we can see here, we have like, let's say R1, R2, they're connected to each other. This is not necessarily an internet-based connection. This could be like from a site to site, but that's a WAN connection because it's connecting two routers which have their own local area networks hanging off of it. So a WAN is essentially a network of networks, and then the internet would be the largest WAN, your WAN connection. Your WAN connection, we use it in our NOC environments when you're on the job. Say, hey, we gotta go, our WAN is down. That means our connection to the ISP is typically down, okay? That's what it, like day to day, as a network engineer, where you may hear that term. I'm gonna move on from this definition. SOHO, small office, home office. So this is gonna be a simplistic network that focuses on cheap availability for the customer. So imagine you work at a managed service provider and you have a small company like the smoke shop I have next door to me that says, hey, I want someone to manage our IT. And you say, okay, what do you have? 2 employees, 1 point of sale machine, and some cameras. More than likely as an MSP, no matter what I charge them, even if I hit them over the head, I'm just going to go to Spectrum, the local ISP, and say, hey, give me a router, right? I mean, that's typically it. Maybe I'll add some additional things in there, but that's a SOHO. It's a network that enables multiple users to share a single broadband connection. So different than like our enterprise-grade WAN connections where we may have 3 forms of transport like MPLS, a broadband connection, and like Starlink, and we are paying all that expensive MPLS dedicated circuit connections. SOHO is like, hey, just go to local ISP, get what it's available. We don't need business grade 2.5, 5 gigahertz fiber, 5 gigabits per second fiber in here. Now we're getting into our campus networks, our big topologies. So we're going to talk about our 3-tier core topology. So this is a network design put out by Cisco that lays out how a large campus network should be built for the best performance and management and a good structure when talking about our enterprise-grade switching technologies. So we have 3 layers in our 3-tier core topology. And I always tell people this, that yes, this is probably the best way that Cisco came up with to lay out big campus networks, but it also just happens to be in line with what they sell as far as catalyst switching and enterprise-grade switching. They sell access, distro, and core switches, right? I'm going to bring up something on Google right here to show you guys what I'm talking about. So let me bring this into view. So you see these different catalyst switches. That's the current like catalyst switching. So when they sell like this switch right here, they'll call that the access switch. And it just so happens, oh, you have a big enterprise. Well, that means you need to follow our 3-tier, which means you gotta buy our distro, and this is probably like the core switch right here. So it kind of goes in line with what they're selling. I'll try to bring up a different. I used to have the direct link to this in my bookmarks, but there's a good image. I'll try to find it maybe our next break that shows you all 6 of their offerings and how they label them, like access, distro, and core. Anyways, let's actually get into this though. So what we need to know for the exam, because I always got to remember we're here to pass a CCNA exam. Okay, so 3-tier core topology. We have the core, distro, and access layer. So the core layer is going to be the biggest and fastest devices that aggregate all traffic out towards the internet. This is going to be real beefy switches with a lot of compute resource. Typically, you're going to look at it with like 40 gig, 10 gigabit connections like twin-ax or, really heavy-duty 40 gig Cat 8 connections, multi-mode, single-mode fiber. The port density doesn't have to be as dense as like our distro would be because we're doing this as an aggregate for a strong backbone, okay? With these switches, they're going to be like probably 8 16U stacks. When I say 16U, that means if you look at like a data center rack, a single U, we're talking 16 of those. 8, 24, maybe not 24 yet, that's kind of big. But like a 4 8U stack core layer switch is what that's going to look like. It's typically going to have like a supervisor engine in it that's going to be controlling all the different blades in there. Now, distribution layer. This is going to provide policy-based routing for all of our internal traffic. It's kind of that middleman between the access and core layer. So it's going to push all of our user traffic up to the core layer. But internally on our campus, when users are talking to other users, we're making phone calls within our office, our campus network, all of that wireless is going to be done at the distro layer and down. So distro layer does routing for all internal traffic, applies filtering and ACLs, and routes traffic between your subnets and VLANs. Then our access layer, typically layer 2 switches, doesn't mean they have to be. This is where our end devices connect to. End devices connect to the access layer. This is our printers, VoIP phones, laptops, computers, desktops, access points. Any kind of end device is typically going to go to the access layer. Now, as far as servers go, like if you have like one-off servers, comms closets full of tower servers, sometimes that can sit at the access layer. But typically your data center, like let's say you have a data center rack, maybe that Nexus switch would be connected to the distro layer to route out to the internal net, and then they would have another connection to the core layer for the internet. Now, I'm not big in data center design, but if you have a little web server farm maybe you manage for your campus, that would more than likely be at the distro layer. Now, to sum it all up, the 3-tier core topology, that's going to be for large enterprises. If you have a large growing enterprise, that's a 3-tier. That's the topology you may want for your campus networks. Now, collapse core. Going over 3-tier core topology kind of helps us understand a collapse core better. That's for our small to medium-sized businesses with maybe minimal potential growth, but maybe they have a set 300 to 400 users. Like, hey, this is what the company is for the next 2 to 3 years. So we don't want to hit them over the head selling them multi-million-dollar data center enterprise builds. So we say, hey, take that distro layer and have that, or that 9400 series catalyst switch, and combine that. That's going to be your core and distro switch. So collapse core just combines the core and distribution layer, while the access layer stays the same. Spine and leaf topology. So this is, I want to say new, but it's been around for a while. So spine and leaf topologies, I'll say it. It's a new topology as far as like Cisco is concerned and then Cisco Learning. And this is going to be built for data centers and our SDN architecture. That's why it was made. Spine and leaf architectures don't need spanning tree protocol to prevent any sort of broadcast or switching storms. And in the spine and leaf architecture, devices are separated by the same number of hops. So every single leaf switch here will always be one hop away from another leaf switch. So the spine layer here is going to be where our beefy switches are. And this spine and leaf topology allows for consistent latency among our network devices. That's a key thing I want you to memorize. That spine and leaf topologies allow for consistent latency among network devices. Full mesh topology. Yeah, I'm skipping a little bit, guys, because we have 5 days, so I don't want to dive deep on maybe something that won't be on the exam. But a full mesh, something you have to know. A full mesh topology is when every network node is fully connected to each other with a system or domain. And we're going to end it there. We don't need to go over a bus topology. All right, so that was section 1.0.6, network architecture. Now let's go ahead and go over the control and data planes. And then we'll take another break once we go over this slide, okay? Okay, control and data planes. So to understand traditional versus controller-based networking or software-defined networking, we need to talk about the different planes that exist on our network infrastructure, on our network devices. So in traditional networking, I take a router out of the box. I get on the CLI and I configure it. It's going to have what's called a control plane and data plane. There's also like the management plane that we're not going to talk about here. The control plane is going to be all the technologies and protocols that we configure that gives that device some intelligence. Now, I'm not talking like AI. What I mean by that is when I configure OSPF, a routing protocol on a router, that OSPF protocol is going to determine how we forward. It's going to build a routing table for us. And us as an administrator, we go into the CLI and configure OSPF. And we make changes to OSPF. We configure advanced features of OSPF in the CLI on that device. That technology is called the control plane. And when the control plane sits at that individual device, it looks like an island. It looks like its own little island that talks to all of its neighbors. The data plane on that device will always stick to that device and will always be on that device, And the data plane is the actual incoming, it's the ingress and egress of that traffic. The data plane is the actual bits coming in that wire and coming in and out of that device. Now with controller-based networking, the control plane and the management is done from a centralized server. So we take away that control plane from the individual device and centralize it in one of our SDN offerings, and we call that controller-based networking. Well, now from a single pane of glass, from like our Cisco Catalyst Center, SD-WAN, or our SD Access offerings in Cisco, we control all that fabric underneath. That's still our hardware where the routers and switches and access points live that are forwarding data, but now all the intelligence is being brought into a control layer or a centralized controller. So controller-based networking, the control plane management is done from a centralized server which manages the routing and switching policies for all of our what we call fabric devices. So just to take a deeper look at the control plane, so control plane technologies at layer 2 consist of Cisco Discovery Protocol, Dynamic Trunking Protocol, things like VTP, which stands for the VLAN Trunking Protocol, and Link Layer Discovery Protocol. These are all protocols that help layer 2 devices do discovery and interact with on the network. That's control plane technologies. Layer 3 has routing protocols and different protocols like SNMP, OSPF, RIP, ERGRP, all routing protocols, MPLS. That's all control plane technologies and protocols that get centralized in our routing. So we look at traditional networking. All these switches here will have their control and data planes. A controller-based networking, all the switches here, their data planes are still the same. Frames are still being forwarded at the actual switch level. They're still going to have their forwarding tables, but all their control, how they learn, all their control plane technologies are now at a single network controller. So the data plane, take a deeper look at the data plane. Let's look at a router here. So the data plane is where the actual data gets forwarded interface to interface. So we see in a traditional network, we have a control plane. We enable OSPF. OSPF creates a neighbor table. It creates a link state database table. All these tables and caches are necessary for the protocol to actually build our routing table. And then that routing table is part of our control plane that tells the router how to forward traffic. That information gets pushed down to the data plane, which has a forwarding table that'll quickly switch incoming traffic inbound and outbound in a router or in a switching device. So this forwarding table gets built from our routing table, which can also be looked at as a control plane building the data plane table. Now, in controller-based networking, this is still happening, but instead of this function being at the local device, it's going to be at a centralized controller. All right, awesome. Let's go ahead and take another 10-minute break to give you a little breather, and then we'll get into the OSI model, okay? Okay, let's go ahead and get back into it. So now we're going to go over the OSI model. So the OSI model, I'm sure we've all heard of it. If you've done any kind of work in IT, it's how we describe the different layers of encapsulation that a data packet goes through. So it was created in 1978 and was officially published by ISO, the International Standards Organization. So this describes the encapsulation and de-encapsulation in the different layers of which data is going to communicate over a network or computer systems. So you can see here, one thing I want to let you guys know, like, this is encapsulation from the application down. That always confused me. I don't know when I started out. I thought for some reason encapsulation started at layer 1, but no, it doesn't. If you think about when I spin up Zoom, I open up Zoom, and I hit start. That application is where I start, and then getting it to you, to the Zoom web server, whatever the destination is, I encapsulate down from layer 7. I go from my application Zoom to my presentation layer to my session layer, which is like the TLS session and connection to the destination, my transport layer, down to my IP header, to my Ethernet header, and then all the way down to how those bits are going on the wire. And then de-encapsulation is the way back up to the application. That always confused me, so I always just like to put a little preface out there. Okay, so here's the OSI model kind of broken down. So as a network engineer, we typically stay in like layer 5 and below, with the session layer kind of being where we have our TLS, different APIs we may interact with, especially today's network engineer, where automation and REST APIs and programmability is a big part of our job. But typically, traditionally, it was always layer 4 and below, where we made sure that the TCP session made it to the web server and we were good to go, right? Nothing was getting blocked. We made sure that our routing at layer 3 was good. We made sure that our switching and our LANs were good at layer 2. And of course, we made sure that layer 1 was good before we made a help desk ticket, right? Anyways, so this is the OSI model. We don't need to focus on memorizing it really for the CCNA exam. I'm just going to go through layers 1 through 4 more in detail in the following slides. When it comes to the data, the physical layer, that's layer 1. That's going to be our physical, that's going to be the medium on which data traverses. And what we mean by that is, that's our cabling, that's Wi-Fi, that's even antennas shooting to a geosynchronous satellite in the sky. That's our copper cables. Layer 2, the data link layer, that describes our switches, frames, MAC addresses. That's all layer 2. Layer 3 is our network layer. That's going to be all of our IP addressing. That's going to be routers. That's going to be our IP-based packets. And then layer 4, our transport layer, that focuses on our end-to-end communication and connections. That's going to be the TCP and UDP protocols. How we actually arrive at the destination. Are we arriving intact? That's layer 4. So layer 1 is where most troubleshooting begins when it comes to doing like basic network administration. At layer 1, you'll see typical errors like CRC, cyclic redundancy errors, where, I don't know, maybe things are coming in fragmented. We may see some EMI, some errors there. Distance factors. So a cable that can't go on forever, right? So we may have some attenuation based on the distance of our cabling. Or we could have incorrect transceivers. So incorrect small form pluggables, like for fiber. So the major layer 1 connections we're going to talk about is copper and fiber. So with our copper connections, typically what you guys see as Ethernet cable is going to be in different categories. That's like Cat 5 to Cat 8. And those copper cables are going to come in unshielded and shielded twisted pairs. With unshielded twisted pairs having those copper pins with no protection from any outside interference or EMI. And then shielded twisted pair, we're going to have that like cladding or that like aluminum foil to protect us from EMI. Unshielded and shielded twisted pair copper cable gets crimped into what's called an RJ45N. And those RJ45Ns with our STP and UTP have different category levels that will define the different speeds and distance. So it's like Cat 5, Cat 5E, Cat 6, Cat 6E or A. We also have coax cable down here, which you see a lot like in our modems. They're going to have different standards as well, like RG11, RG56, 57, 58. We don't need to get into that for the CCNA exam, though. How we crimp our UTP and shielded twisted pair cables. We're going to have two major standards called T568 Alpha and T568 Bravo. What you see on the screen here is T568 Bravo, where we have orange, white, orange, green, white, blue, blue, white, green, and then brown, white, brown. In fast Ethernet speeds and Ethernet speeds, so Ethernet being 10 megabits per second, fast Ethernet being 100 megabits per second, pins 1 and 2 will be transmitting, and pins 3 and 6 will be receiving. While the other two pairs, or four of their pins, 4, 5, 7, and 8, will be doing our power over Ethernet if we have that available on our switch or on our hardware. Power over Ethernet is how we send wattage to PoE-enabled devices like access points or IP-enabled cameras. When we get up to gigabit speeds, which is going to be 100 megabits per second, all 8 pins are used, all 4 pairs are used for our 1000 megabits or gigabit per second speeds, and then PoE is going to use all 4 pairs as well. Real quick, let me bring up Secure CRT, and let's get into a Cisco Catalyst 9300 series switch, and let's check this out a little bit. So I'm going to show you guys something. When we want to look at, let's zoom out a little bit. Let's say we want to check the PoE on this switch. We can do this command show power inline. We can see the available wattage, and we can see these gigabit Ethernet speeds are able to apply that wattage. Now, I talked about how Ethernet and fast Ethernet, only pins 1 and 2 will transmit and pins 3 and 6 will receive, and the other 4 pins won't do anything unless we have PoE enabled. So let's do a quick test here. So if I type in show interface status, include gig 6, like I got this in, let's see our connected. So this is our trunk port. This is going to, like, I think a IP-based camera, and these two are disabled. Hold on, my cameras are off right now. Sometimes when I record, I turn them on. I'm going to turn my cameras on. 6, include connected. Let's do this, connected. So here's all my available interfaces that are sending traffic. Let's do a test here. Let's do a test to see if this interface is actually truly doing gigabit speeds. Because you look here, you see how these ones are auto to 100 megabits per second? So I wonder why. So we can do a test from our switches here. We can do test, cable diagnostics, time domain reflection, interface gig 6/0/48. So it's going to do a test. And then if we do up arrow, I hit Control A to bring me to the front here. And I do show cable diagnostics. The test isn't done yet. Okay, so look at this, guys. You see where it says short here? So that means that the RJ45 that got crimped, pair C and pair D, which I'm assuming is going to be pairs that we don't need for fast Ethernet to be able to happen, right? They're short. So that's why we're not getting our full gigabit Ethernet speeds. Even though the cable there should be able to, it's like Cat5e, which can go up to a gigabit in speed, and this is a gigabit Ethernet port, we're not actually getting those speeds. So you may think that you crimped correctly because something turns on, you see it get power, you see it's passing traffic, but look it, it's short on these pairs. So we're not able to get our full speeds. So it's kind of cool, that kind of shows us why we, for some reason, are going at 100 megabits instead of a gigabit. And it's not a cabling issue. Well, excuse me, what I mean by that is we crimped them bad, right? And when I did this, it's just for this is going to something local. I don't really care about it, right? This is like my lab environment here. But let's check out this right here, gig 6042. If we do that test. So it's going to take a while to do the test. If we up arrow, and now show the results. Give it a second. But we're going to see that it's a gigabit, 1,000 megabits in speed, and all those pair statuses are normal. This means it got crypted correctly, and all those pairs are in use, and all those pins. So pretty cool. Now moving on to like fiber, I'm going to type in this command show inventory here. So this is a Catalyst 9300 series switch with 48 ports in density. So you guys see this uplink module here, 4x1G uplink module. This means that I have an SFP here, a small form factor pluggable for multi-mode. Well, this is a bay to plug in an SFP, so I can do fiber on this switch. So that command show inventory, I see that 4x1G uplink module. So I can put a single mode or multi-mode SFP in here. So we come back here, okay, we kind of beat it over your head about copper, but now we have fiber. So we have single mode and multi-mode fiber. So in multi-mode, we're going to have this glass core here in our fiber because it's going to be light. So that light goes through a glass core. And that glass core, write this down if you're taking notes, will be about 50 or 62.5 microns. Let me type that out for you. It's going to be about 50 or 62.5 microns for multi-mode glass core. And it's going to be multiple streams of light bouncing up and down. Multi-mode is for short distance. Now, short distance is fiber is something like 550 meters max, okay? That's a short distance. So we use multi-mode like within like our data centers and things like that. Well, with single mode, it's going to be 9 micron glass core and long distances. Up to even 70 kilometers depending on what type of single mode, okay? Now, single mode typically is going to be like a yellow cable with multi-mode being an orange cable. Now, multi-mode and single mode can both have a bunch of different connectors and transceivers on them for multiple different SFPs that will plug into your actual network device. So here I just have an image of 4 common ones, LC, SC, ST, and FC. All can be, any one of these connectors can be for multi-mode or single mode, but it just depends what you have in your environment, okay? All right, moving on. So now layer 2. So layer 2 communication is all based on MAC addresses. So a switch is the layer 2 device that will forward frames based on destination MAC address, which I went over in great detail before lunch. But let's take a look at the MAC address table on a real Cisco switch. Now, when you guys are doing your labs tomorrow, you're going to get a real Cisco switch too. It's just called a viral IOS. So it's a virtualized switch. This is an actual Catalyst 9300 switch. So if we see show version, yeah, this is iOS XE. I know anyone maybe, because I might upload this to YouTube. Everyone's watching. Yes, I know my iOS is old. Anyways, but this is my version, Catalyst 9300. You can do that with the command show version. It'll show your iOS as well. Okay. Why did I bring that up? Oh, let's look at our MAC address table. So we type in show MAC address table. This is going to show you all the MAC addresses that are connected. So you see how there's a bunch of MAC addresses on gig 6/0/42. That's to an access point, okay? This is all the computers that are connected to an access point I have here in my little lab environment. All right, awesome. So show MAC address table. If you're ever looking for a specific MAC address, you can do this pipe command, and let's say I'm looking for this computer here, 8EE6, and it'll show me exactly that and what port it's hanging off of. Then if I want to go look at what that port is configured as, I can go take a look. Now, obviously, this is my little lab environment, so I'm not running any VLANs or anything crazy like that, okay? But that's what the MAC address table looks like. Okay, layer 3. So layer 3 communication is all based on IP addressing. A multi-layer switch or router is going to be the layer 3 device that will forward packets based on the destination IP address. So layer 3 devices make forwarding decisions based on the best IP router prefix they have in their routing table. Okay, in layer 4. So layer 4 is going to be the end-to-end communication of an IP packet. Our layer 4 header is going to be either TCP and UDP, and that's going to ensure end-to-end communication. Now the difference, TCP is connection-oriented, while UDP is connectionless. Or you can describe it as TCP is reliable and UDP is unreliable. So now the question is, when do we choose to use one or the other? Well, some applications that are in real time, meaning you're talking on the phone, streaming video, they want an unreliable connections. I put quotations up because it's still reliable, it still gets to the destination. But with UDP, we don't establish a data channel that ensures every single bit in a data packet reaches its destination. If we had that, we could never have a phone call because the moment we miss a packet, it will drop the phone call. With UDP, it's best effort, meaning even if we know we have a little bit of packet loss, we're still going to send that data to the destination. With TCP, that's not true. When we do a TCP connection, from sender to receiver, from source to destination, before we actually have an established connection, we do something called a three-way handshake. That three-way handshake involves step 1, sending a SYN flag, which is from sender to receiver saying, hey, I want to initialize a TCP connection with you. That receiver or that destination or that server will send a SYN acknowledgement back, the SYN flag saying, hey, sender, I'm going to initiate a TCP connection with you, and I acknowledged your SYN. Then the sender will send an acknowledgement back. The server will receive that, and they together now, client and server, are going to establish a TCP data connection. And that data connection is going to increase in how much data is being sent, like 1 megabit, 2 megabits, 3 megabits. And once we get to a state where we start noticing packet loss, the TCP connection will break, we'll redo the TCP connection, and start our data stream over again. Now, we don't want that with like YouTube videos or Zoom calls, because the moment you guys hear the crackle in my voice because there was some interference or latency in our connection, the Zoom call would restart. We're doing UDP here because it's going to keep sending its best effort no matter what. That's why we say it's not reliable, quote unquote, but it still ensures you get to your destination. We just don't have an established data channel that has no room for loss. With UDP, you have a little room for packet loss. As far as the exam goes, guys, you just need to remember this last bullet down here. TCP is connection-oriented, it's reliable, UDP is best effort, it's unreliable, and it's connectionless. There's many different ways they could ask you the differences on the exam. Now, with TCP, it's always going to be unicast. I mean, it's going to be one-to-one. It's always going to be that client-server architecture, or client-to-client, or server-to-server architecture, one-to-one. Now, with UDP, we could be unicast one-to-one. All of our broadcasts are UDP, so if we're a single node that needs to talk to every other node in our subnet or network, and we broadcast, the layer 4 header is going to be UDP, and it's going to be a broadcast. If we need multicast, one-to-many, where I'm a single node sending a video stream or a stream of data, and only some nodes are going to listen to it, that layer 4 header is going to be encapsulated with UDP. All right, awesome. It is 1:15. Let's go ahead and take another 10-minute break because my voice is just weak, guys, sometimes. I've been teaching for like 4 weeks straight, so I need a little bit more breaks than usual. We'll come back at 1:15. We'll come back at 1:25. We'll take a 10-minute break. We'll go over IPv4 and IPv6, and then we're going to call it for the day, okay? So we'll come back in 10 minutes. Okay, guys, let's go ahead and jump into it. So let's go over IPv4 addressing. So IPv4 overview. So you guys have probably seen an IP address at least once or twice in your day. So typically you see it in what's called the dotted decimal format, where you have 4 octets, 4 different numbers separated by a dot or a period, and they're going to be numbered 0 to 255. So an IPv4 address is needed to have a common way for all devices to communicate across the internet, a standard protocol. So that standard protocol in today's world is Internet Protocol version 4 and 6. An IPv4 address is going to be 32 bits. Okay, it's going to be a 32-bit address that gives your network device a unique identity. Now again, you typically see it in this dotted decimal format, where it's 0 to 255 separated by a dot. But each octet is going to be 8 binary bits, which also equal a byte. So we have 4 bytes here, or a 32-bit address. Now we see it in regular human numbers, computers see it in binary. So these 8 binary bits will either be on or off to make up a number. So let's go over binary and decimal conversion. So binary is a numbering system that consists of the numbers 0s and 1 called bits. It's how computers speak. That's really at its raw form how computers communicate with each other over binary. We use CPU uses binary to compute things. It's binary. So the decimal numbering system, in contrast, consists of 10 digits consisting of numbers 0 through 9, where binary is just 0 and 1. The 0 bit meaning off and the 1 bit meaning on. So each address, IPv4 address, consists of a string of 32 bits divided in those 4 sections. So when we want to convert 8 bits into a single whole number for our dotted decimal format, here's the chart you need to memorize. So as you can see here, if we're trying to convert these 8 bits into a number, into a dotted decimal format, we line it up against this chart here, or that positional value, 128, 64, 32, 16, 8, 4, 2, and 1. We take those 8 bits and from left to right, line them up. If we have a 1 bit, which equals on, that means we're going to take that positional value. So we have 2 ones here at the start. So this one's going to equal 128, and this one's going to equal 64. The rest are zeros, meaning off bits. So we don't take those positional values. So in total, once we add up those positional values, our whole number is 192. So anytime we convert binary to decimal, or decimal into binary, we use this positional value chart, our binary to decimal conversion chart. So we can see it here again. Let me bring out my pen here. So as you can see, if we want to convert these 8 bits, we line them up against this chart here. So if I want to do this myself, I'd make my chart. So let me take this one right here, these 8 bits. I'd line them up 0, 0, 0, 0, 1, 0, 1, 1. I'd bring those down. My positional value here is 0 because it's an off bit. My positional value here is 8, 2, 1. And then I add up these, and that's going to equal 8 plus 2 is 10, plus 1 is 11. So this octet right here in binary is 00001011. If we take that, put it against our binary conversion chart, take only the on bits as positional values here, add them up, we get our dotted decimal or whole number. So if I do that again, so I'm going to clear this. So we know this first octet is 192, this third one's 11. So let me clear this up, let me do the second octet. So I'm going to take my chart, okay, and let's line up this second octet. So it's 1, 0, 1, 0, 1, 0, 0, 0. And try not to fall asleep behind that screen. I know this is very mundane and just crazy boring, but it's the fundamentals. So let's take our positional values. So we have 128, 0. 32 on bit, off bit 0, on bit. The positional value is 8, 0, 0, 0. And now let's add these up. 128 plus 32, that's going to equal 160. 160 plus 8, that's going to equal 168. So the second octet is 168. Now let's clear this. So it's 192.168.11. Now let's convert this last octet here in binary to decimal. So I'm going to put my chart again. And let's line this up. So 0, 0, 0, 0, 1, 0, 1, 0. So all zeros here, so I'm not even going to write that. This positional value is 8. This one is 2. So 8 plus 2 equals 10. So my full IP address here, now that I converted all this binary to decimal, is 192.168.11.10. And that's how we convert. Now what we're about to do is do it in reverse. And what we mean by that is, now let's convert decimal to binary. Let's do it. So here's how we say we do it here. I'm just going to ignore this. So is the decimal n greater than or equal to 128? I don't like the way to describe this here because you're bad at math. This ain't going to make sense. So let's go ahead and bring up a whiteboard. Okay. So how do we convert decimal to binary? So we're going to do decimal to binary now. So here's how we do it. So we're going to get our whole number here. Let's say we want to convert the number 174. We want to convert this to binary. First thing, we're going to write our chart. 64, 32, 16, 8, 4, 2, 1. So now we're going to take that number, and here's what we're going to do. We're going to put it above 128 here, 174, and we're going to say, is 174 greater than or equal to this positional value? Well, it's greater than. So that's an on bit. And then we're going to minus that. So 174 minus 128. I'm going to bring up my calculator because I'm not good at math. But 174 minus 128. That equals 46. So 174 minus 128 is 46. Okay, so we take the sum after this subtraction. So if our number is greater than or equal to this positional value, we start left to right. So we start at our highest number here in our binary to decimal conversion chart. It's an on bit. But we got to take away that though. So 174 minus 128 is 46. Is 46 greater than or equal to 64? It's not. It's less than. So guess what that is? Off bit. Now is 46 greater than or equal to 32? It's greater than. So guess what? That's an on bit. And then we got to take that value away. So 46 minus 32, that is 14. Is 14 greater than or equal to 16? It's not. It's less than. So that's an off bit. Is 14 greater than or equal to 8? It's greater than. So that's an on bit. And then 14 minus 8 is going to be 6, I believe, right? Yeah, 14 minus 8 minus 4 is 6. Is 6 greater than or equal to the number 4? It's greater than. So that's an on bit. 6 minus 4 is 2. And then is 2 greater than or equal to the number 2? It's equal. So that's still an on bit. Then we do the subtraction and the rest is 0. So in binary, the number 174 equals 10101110. And that's how we convert decimal to binary. Okay, now let's move on. Now let's go over our IPv4 address structure. So an actual IP address. So when we say my computer has an IP address, that's going to be the unique IPv4 address of the host. So that could be a router's default gateway. That's a unique IP address. My computer's IP is a unique IPv4 address. The subnet mask. The subnet mask or prefix is sometimes what we call it, is used to identify the network/host portion of the IPv4 address. So the subnet mask lets the device know that this IP address is part of this larger network or subnet that is shared with other nodes. Okay? So here we have what's called a /24 subnet, and we'll get into subnetting on your homework tonight because I want to give you guys a little brain break. Like, I don't want to go till 5 o'clock doing subnetting. I'll just be honest with you because your brains are going to be fried, and we have a long week ahead of us. But this is used to identify the network/host portion. So the ones in the subnet mask identify the network. The zeros identify the host portion. So if we have all zeros here in the subnet mask, so 255.255.255.0, which means, and the binary value is all zeros. If we add those up, that equals 255. Because we're going to put that to our chart. You'll see it in the subnetting videos. Anyways, so that means this host is a part of this network that ranges from 0 to 255. The default gateway. This is going to identify the local gateway of your routed device or your routing device. This could be an actual physical router, or this could be a multi-layer switch with a switched virtual interface that gives it IP addressing, and that could also be your default gateway. Okay, prefix length. So the prefix length or subnet mask and your CIDR has a correlation. When you see /25, that means there's 25 network bits in the subnet mask. So that means all these ones, that's the network portion, and then in the /25, the rest of these zeros, if we add those up, that's going to equal, like compared to our chart, that's going to equal 128. So a /25 has 128 usable hosts. A /28 means we have 28 network bits, which means if we add the rest of those host bits up against our chart, we're only going to have 16 available IP addresses in that mask. What I mean by adding them up too, we just write our chart out again. 128, 64, 32, 16, 8, 4, 2, 1. And we're talking about subnets now, subnets. If I have a /26, that means my subnet mask has 26 network bits. So a /26, that's the actual subnet mask. This is my host portion here. If I put those zeros up against this chart, because, right, these are network bits. If I take all these and add them up, that's going to equal 64. So that's going to equal my network range /usable IPs, okay? More on that to follow when you guys do your homework tonight. Okay, so in a network or a subnet, we're going to have a network address, then we're going to have the first and last usable IP address and a broadcast address. The network address is going to be the delimitating thing, the delimiter that says this is the start of the network. Don't use this. You cannot assign this IP address. I'm saying that .0 is the start of this network here. And then our first usable will be .1. Our last usable in this network is .254. And then this broadcast address is also designed to not be assigned because every single node should be able to send traffic to this IP address if they want to address every single computer in the subnet, or every single node in this subnet. So every subnet or network is going to have a network address and a broadcast address. That'll be the very first IP, the very last IP. And then we're also going to have a first usable and last usable. Typically, that first usable is going to be the default gateway. Typically. And remember that default gateway, we have a router with a switch here, and we got users. This is going to be our default gateway here. This interface hanging off the router. Because that router is what we need to talk to when we need to talk to anything outside of our LAN, like out to the internet, anywhere outside of our LAN. That's typically where the default gateway lives. No, that is where the default gateway lives when on your router or whatever your routing device is. And commonly, the default gateway will be that first usable. However, I've been in environments where it's been the last usable. The default gateway doesn't have to be the first last usable. It could be a random IP. It could be .100. That's just not common practice because it doesn't make a lot of sense, right? Okay. Different IPv4 communication types. So we have unicast, broadcast, and multicast. This is the 3 different ways IPv4 communicates. So unicast is one-to-one, broadcast is one-to-all within a network, and multicast is one-to-many. Multicast is I'm sending a stream of data to a multicast address, and if you want to listen to it, then listen to it. But if you don't have to. That's how multicast works. Think of it like the radio, where your car needs to tune to 92.3 to listen to that station. But if you don't tune to it, does it mean that the radio waves are not being propagated? Yeah, they're being propagated. You're just not tuned to it, so you may not hear it. Multicast is the same way. If I'm sending a stream of data to a multicast address of 224.2.3.22, I'm sending that out at all times. But if I'm PC1, maybe I listen to it. But if I'm PC2 here, I don't have to. So that means I don't hear it. I don't see that data stream. Okay, classful addresses. So we have our different classes. So class A is this address block 0000 to 127.000. We have class B, class C. Go ahead and take a look at them, guys. And then class D, this describes all multicast addresses. So class D, this is specifically designated when you want to do multicast addressing, okay? That's the only one I'm going to make a little caveat here for, okay? Class D is multicast. So if you're setting up a streaming server and you want to do multicast, you need a multicast address. So an address within this range, okay? Private IP addresses, let's go over them. So RFC 1918, Request for Comments 1918. That is a standard that describes IPv4 addresses. So ISPs worldwide, internet service providers that allocate IP addressing, they get their number registrations from an organization called ICANN. Anyways, private IPs or RFC 1918 addresses are classes of addresses that cannot be routable on the internet, are only used for internal use. More on this later when we talk about network address translation, probably like day 4. But private IPs are not routable on the internet. They're only used for your internal LAN and network, and they protect you from exposure, and they allow us to not run out of IPv4 addresses. Because IPv4 addresses, we ran out of unique ones a long time ago. So if everyone in this class right now goes to their command prompt and types in ipconfig, more than likely, we're all going to have an IP address like this, 192.168.0. something. And all of our gateways may be .1. And you may say, how is that possible? We're all supposed to have unique addresses, aren't we? How can we have all these IP conflicts? Well, that's because that 192.168 is a private IP, which is not routable on the internet, and every single LAN can have the same private IP address range without any conflicts, because at your router, at your WAN, you do have a unique public IP that translates all your private IPs. More on that later again. But private IPv4 facts that you need to know for the exam is that private IPs are not routable on the internet. They provide an added level of protection against internet exposure because your computer technically never, its source IP never touches the internet because you have a private IP on your computer. Multiple companies can use the same private IP addressing, makes things easier for us. And we don't have to register those private IPs with any organization like ICANN or another organization called IANA. It's like International Associations of Numbers, something. They're not registered, okay? So that is private IPs. Okay, then we have some special IPv4 addresses we're going to talk about. So the loopback IP is 127.0.0.8. This is used to test NICs. This is used to like host local like web servers and do local testing. And a PIPA address is something unique to Windows, where a Windows computer doesn't get an IP address from a DHCP server, so it self-assigns one, and that's called an PIPA. All right, awesome. Now, let's quickly go over IPv6. Not quickly, but let's go over IPv6. I'm going to touch on things that are going to be on the exam. And then we're going to end class today. And I'm going to send you guys a message in Signal going over what I want you to do for homework. And I'll show you on the screen before we go. But IPv6. So IPv6 does the same exact thing as IPv4. It gives you a unique address to communicate on the internet. They say there's like enough IPv6 addresses for every grain of sand on Earth, whatever. IPv6, every single computer can have its own public address. They don't call it that in IPv6. They call it global unicast. Some comparison, though. IPv6 address is 128 bits. And it doesn't need technologies like network address translation because we don't need to have this public-private IP architecture. IPv6 is represented in hexadecimal. So IPv6 addresses will be 0 through 9 and A through F, just like your MAC address. It's 128 bits in length. And you're going to have these hextets that are separated by colons. So you're going to have 8 hextets. And each hextet's going to have 4 hexadecimal digits in it. So here's just more IPv6 addressing. Here's the chart. So now when we want to convert from decimal, hexadecimal to binary, here's how it looks. So a decimal, our regular numbers, we go 0 through 15. And hex, we go 0 through 9. And then once we cross into the 10 territory, we go A, B, C, D, E, F. This is something you're going to have to recognize, okay? These letters equal this in decimal. Now with hexadecimal, each digit is 4 bits. So in hexadecimal, when we convert that to binary, it's 4 bits. So our binary chart looks a little different. It's just 8421, 0110. And then we bring that down. 4 plus 2 equals 6. That's how we do binary to hexadecimal conversion, okay? It gets a little tricky when we look at this because we put this against our hex to binary conversion chart. 1, 1, 1, 0. Bring that down. 8 plus 4 plus 2 equals 16. Or not 16, sorry. 8 plus 4 is 12, plus 2 equals 14. But in hexadecimal, that equals E. So you got to know this chart, okay? All right, now let's go over some IPv6 rules. So as you can see here, IPv6 is long. It can be really hard to type out. There can be prone to human errors in IPv6. So we have rules. We have these IPv6 rules that can reduce or compress IPv6 addresses. So the first rule is that you can omit leading zeros. So as we see here, here's our original IPv6 address. If we want to shorten it or compress it, all these leading zeros we can get rid of. So our new hextets can just be 0. 0, colon. But notice it's only leading zeros. So in this last hextet, we have 0200. We only get rid of the leading zeros. So now this new hextet is just 200. So that's one way we can compress our IPv6 addresses. Rule 2. We can omit all continuous 0 segments one time in our IPv6 address. So notice in this IPv6 address, it's 8 hextets, and we have 2 hextets here that are all zeros, and then 2 hextets here that are all zeros. So what we can do is either right here, convert this to a double colon, or not and, or convert this one to a double colon. But we can only do it one time. So we have two correct ways to compress this. With a double colon at those first hextets, or a double colon here. But you can only do a double colon one time. And then notice, we can take our first rule though, and still get rid of the leading zeros. So you can put a double colon for any continuous string of zeros in 2 or more hextets, okay? So like, let's say this was all zeros too. We could represent all 5 of those hextets with a double colon if they're all zeros, okay? Double colon can only be used once, and it can be used for a continuous string of zeros in 2 or more hextets. We don't get into that. Packet header is not important. Okay, so let's get into the different types of IPv6 addresses, okay? So you're going to need to know this. So a global unicast IPv6 address. That's like a public IPv4 address. It's routable on the internet, and it gives your device a unique IPv6 address. So global unicast, the range is going to be the first hextet here, 2000 to 3FFFF. So if you see an IPv6 address and the very first hextet is any combination within this range, global unicast. Link local. If you see any IPv6 address and the first hextet is FE80, that's a link local, okay? A unique local, I have it already typed out here. If you see any IPv6 address with a Fox Charlie 00 through Fox Delta Fox Fox, that's a unique local. One that's missing here is multicast. If you see any IPv6 address with the FF0, that is a multicast address, okay? FF0 is a multicast address in IPv6. If you can memorize what I have up here right now, you're going to be, and you know the rules to IPv6, you know how to omit leading zeros and how to compress using a double colon, and you can memorize what I have on the screen right here, you'll be in good shape for the CCNA exam. Okay, we'll just move on here. Link local address. It's used to enable the device to communicate. It's kind of like the private IPs almost on a shared Ethernet segment. You can create a link local instead of giving a global unicast to communicate in your LANs. Moving on. Then global unicast. That's like a public IP address. Then a multicast address, you can see here, FF02, FF02. That's a multicast address. We'll move on. And another unique thing about IPv6 is IPv6 does not use broadcast, guys. It doesn't use broadcast. There's no need. It does use anycast, though. IPv4 can as well. But there is IPv6 anycast. So an anycast address is an address that's assigned to a set of interfaces that belong to different nodes. So you can see this server here has the same IP address. There could be an IPv6 as well. Anycast works for both IPv4 and IPv6. But these can be geographically dispersed. This could be in New York. This could be in Phoenix, Arizona. And they have the same IP address. And our clients will go to the one that's closest, okay? That's what an anycast address is. All right, awesome. So let's go over what homework you guys are going to do tonight. So on the LMS, you guys are going to do sections 1.1.2, subnetting part 1 and part 2. That's all I want you to do tonight. I don't want you to start doing questions. You're more than welcome to. But I want you to watch these subnetting videos, okay? And tomorrow we'll review subnetting, make sure that we're all kind of understanding, because it's going to be important for the exam. But I just don't want your brains too fried. So we're going to end class today. Start time tomorrow is 09. I'll put out some info in the Signal group chat, just a reminder of what videos to watch, subnetting part 1 and subnetting part 2. And that's going to call it for today, guys. Thank you for joining. If you have any questions, please hit me on Signal. And I'll see you guys tomorrow.